Today's video is about vector projections. Before we get into talking about what a vector projection is, I just want to talk about a unit vector or a notation here that is going to be helpful in a moment. So for starters, we're going to define something called a unit vector, which is a vector in the same direction as the original, but with a magnitude of 1. So let's look at this example. Pretend I've got a vector here and I've decided it's 4 units long. That could be 4 meters per second, 4 kilometers, whatever. Okay, it's 4 units long. A unit vector would be one that's in the same direction, but only 1 unit long. So if I broke this up into the 4 chunks, this little part would be a unit vector. So we call the unit vector, it looks like this. The notation is a V, but instead of an arrow on top, it has got this little hat, this caret, okay? It's still a vector, and it's in the same direction as V, but instead of having the little arrow on it, we've got this little hat, okay? And we call this then a unit vector. Obviously, its magnitude is 1, given that it's that's what we're defining it as a unit vector. Now, if the whole thing is 4 units long, then obviously the length is also 1/4 the size of it, and would result in a vector that's in the same direction, but only magnitude of 1. In general, we can talk like this. Any unit vector is going to be a fraction of the original. And in this particular case, the v vector, the unit vector, is 1/4 the size because it's 4 units long. If the vector was 10 units long, then obviously the unit vector would be 1/10, 1 over the magnitude, however long it is. So if we had another vector that was 15, it would be 1/15 of the original. The unit vector, though, is a fraction of the unit of the original, but only a magnitude of 1. Okay, so we're going to need that notation as we move on to projections. Now, before we move on to projections, I want to think about this scenario. So here we are, and we're going to pull our little sister on a sled. Okay, so we've got this rope, which can be represented by a vector, and I'm going to say I'm pulling it with 50 newtons, okay, some force. Now, because I'm sort of standing up and I'm pulling it at this rate, my 50 newtons isn't perfectly pulling in the direction that we want our sister to go, okay? The toboggan's going to go along this black line, but we're losing a little bit of our 50 newtons because we're not perfectly in line with the direction of motion. We're actually lifting the toboggan slightly, right? So the toboggan goes up a little bit. You can imagine it going up a little bit as we pull it along, okay, up a little bit. Some of this 50 newtons is wasted by lifting. Now, actually, it actually helps us when we pull it, because if you lift it up, it gets it above the snow. But the 50 newtons is not in the direction there. If I wanted to be perfectly pulling her with all of my weight, I would move it and be pulling. I'd be like right along the ground, and it would, all this 50 newtons would be in the direction that we want. But we're losing a little bit because we're actually lifting up a little bit as well. Okay, so the question is, how much of that 50 newtons? Oh, by the way, you've all experienced this. When you've pulled something really, really heavy, you don't stand upright to pull it. You would get down, bend your knees, and try your best to minimize that angle, because more of that 50 newtons force is pulling in the direction that you want. Okay, it's the same with pushing. If you're pushing like a couch, you don't just stand up to the couch and push it. You bend your knees, get lower, and what you're actually doing is reducing that angle so that more of your force is in the direction that you want. Okay, so the question is, how much of that 50 newtons is actually being in this direction? And that's what projection is. How much of that 50 newtons is projected in this particular direction? It's going to be less than 50 newtons because we're losing some of it, but it's still going to be pretty good. And of course, the smaller this angle, the better, the more we're going to keep and the less we're going to lose. Okay, so that's what projection is asking for. So the question is, how do we figure it out mathematically? So we're going to look at a scenario, and you can see the example that I have here sort of mimics what I just had there, a 50 Newton force, but we're going to say that there's another vector down here on the 70, that's 70 units long, okay? That 70 is not going to play into effect until the second part of this question. All right, so we've got two vectors, u whose magnitude is 50 and V whose magnitude is 70, and the angle between them is 30. So we've got that scenario set up. And again, I could move these vectors any way we want, but I'm going to sort of mimic the pulling the sled. I want to find how much this is projected onto the V direction. So we call it with this notation the projection of U onto V. The projection of U onto V. It's kind of like the logarithms where we say the log of something base 3, so we come backwards. This is the projection of U onto V. So how much of that 50 is in this direction? Well, another way you can imagine it is imagine a flashlight. So I've got this little flashlight sitting here ready to go. If I shone the flashlight perpendicular to the motion that I want to go, so here it is, my flashlight's not shining this way because that wouldn't be perpendicular or this way, okay? It's perpendicular to the direction of motion. If I shone it up above the scenario, it doesn't matter how high, if I shone it up here, this vector would cast a shadow down onto vector V. And so there, you can imagine this perpendicular line of darkness where this whole measurement here would be the shadow of this V vector onto U vector onto V. And that vector right here is how much of the U vector is projected in the direction of V. Okay? So two ways to imagine it, but that vector, that red vector, is the projection of U onto V. So the question is, how big is that? It's safe to say it's less than 50. How much of it, though, is in this direction? Okay, so how do we solve it mathematically? Well, luckily, because projection is perpendicular to the direction of motion, you're going to get this nice right triangle. And a right triangle, we can use SOHCAHTOA. So we've got this angle here, this known side, the hypotenuse, and the thing we're trying to figure out is this side. So if we were doing SOHCAHTOA, we would use this angle and the hypotenuse and the adjacent side. So adjacent and hypotenuse, I would use cosine. So the cosine of 30 is adjacent over hypotenuse. So the adjacent side is the projection answer that we're looking for over the hypotenuse. So if I wanted to solve the projection side, it's being divided by 50. I'm going to bring it up and multiply it by 50. I can go to my calculator now, and 50 cos theta, of course we could write it like this, 50 cos theta, and the answer is 43.3. So it turns out that of the 50 newtons of force, 43.3 of it is acting in the direction of V, and that's what projection is. So it's pretty good. You can imagine if we change this scenario and open this up higher, the cos angle would be bigger. So what would happen in that case? So we just did 50 cos 30, and we got 43.3. But what if we were inefficient and we stood up more and raised that angle? So 50 cos, let's say 60. So we're inefficient. Well, now only 25 newtons of that force is acting in the direction that we want. And that wouldn't be a good way to pull our sister. And if we wanted to do the best, we of course would minimize this. So we would go 50 cos, let's say 80. So we're getting really, really close down. Oh, sorry, not 80, 10 degrees. So 10 degrees. 80 would be really bad. 10 degrees. We're going to get our knees bent and check that out. And you see how almost all of the 50 newtons is acting in that direction. So that's the beauty of the cos thing, because the smaller cos is, the bigger it gets to 1. We know cosine curve starts at 1, so the cos of 0 is 1. And if we did that, we did 50 cos 0, then all of it would be in that direction. Okay? And cosine starts there, but as the angle increases, cosine gets smaller in a smaller decimal, which means you only have a smaller percent. Okay? So that's how we find the projection. Now, what sort of units do we use? Well, in this case, we say that it is 50, this red vector is 43.3 little v vectors. So remember, um, this this notation means unit vectors. They're little one vectors that are in here. The whole thing is 70 units long, but there are a whole bunch of one little vectors, one unit vectors. And in fact, there's 70 of them. How many of those are we have in the projection, the red one? Well, we have 43.3 of these little unit v vectors. And the reason we need this notation is because the projection produces another vector. Okay? So just like u is a vector, v is a vector, projection is also a vector. So I can't just say it's 43.3. I need a direction. So the magnitude is 43.3, but the direction is in the direction of v. And that's how come this notation is so handy, because I don't need to worry about describing it and saying, well, it's 30 degrees to this or anything like that. I can just use this notation and say it's in the same direction as v. All right. Now, what if we did the opposite? So now we're going to project v onto u. Project v onto u. So I'm going to take my flashlight again and imagine the opposite thing. So I'm going to make a new flashlight. And if I'm projecting v onto u, I need to turn my flashlight so it's perpendicular to the thing I'm shining it on. Okay, so I'm going to shine it this way, and I'm shining v onto u. So I'm going to put the flashlight here, and the shadow will cast on this direction. Okay, it looks like it's going to be less than 50 because there's 50, but we'll find out. Maybe my picture isn't very accurate. So the projection is going to be this vector right here, the projection of v onto u. So we still get a same triangle here, still a right triangle, and we're dealing with the 30, but this time, well, we're going to use still adjacent is the thing we want over hypotenuse. So it's still going to be cosine, but the hypotenuse changed now and is the 70, but it's our projection is this guy here. Our hypotenuse is now 70. Again, that 70 can come up, just like we brought it over here and rearranged, it becomes 70 cos 30, which we punch that in our calculator is 60.6, and u vectors in the u direction. Now, because I've done this math, I've discovered that my picture isn't very accurate, because it turns out the unit vector, the u vector is 50. So that u vector should have been smaller, because apparently when you project it on there, it's bigger than the u vector. Okay, but that's okay. These are the sketches that we didn't know. You know, we tried to guess how big 50 was and 70. Turns out that blue vector should have been a bit smaller, but no big deal. Okay, so two separate questions here: projection of u onto v and v onto u. So in general, you'll always end up with the same right triangle, and you'll always end up finding the hypotenuse and the adjacent, which means all projections can be found by taking the u vector cos theta. Take the vector that you're using and find the angle between it and the actual projection you're going on to, and you'll get your magnitude of the projection. Since projection produces a vector, we need this little v thing to describe its direction. Now, there is something called a component, and a component of u onto v has no direction. So if we just wanted to know how big that vector is, we call it the component. If we want to know the actual projection, we need that vector notation. Okay, so component is exactly the same thing, just with no direction. All right, so now what we can do, I'm actually going to cover this up. Now what we're going to do is take this and try and do it without the picture. That's why I've covered up the picture. So we're going to try and do this and just use the formula and see if it works. So here I've given angle A is 15 and angle B is 20. And the angle between them is 130. So let's just use our formula. So the projection of A onto B means we're going to use A cos B. A, the magnitude is 15, and the angle between them is 130. So 15 cos 30, 130, and we end up with a negative number. which I'm going to deal with in a second. What's the units for this? Well, it's being projected in the B direction, so we need a bunch of little B unit vectors. So why is it negative? I mean, this is our first time using this formula, and we end up with a negative answer. Well, it has to do with that picture that you may have saw when I turned the page. So let's think here. I've got vector A is over here, and vector B is over here, and the angle between them is 130. So let's try and imagine the projection. So the projection, we're going to spin this around because we need the projection to be 90 degrees, or the flashlight to be shining perpendicular to the direction we want to go. So it's perpendicular to this. So if I shine the flashlight up here, I'm not actually getting the shade or the shadow of the A vector. So I'm going to shine it over here, and the shadow then ends up going outside of this. So we're going to imagine this vector being in the opposite direction, and we see the shadow is backwards. And so our projection is actually in the opposite direction to B, which means our angle is negative. And you can imagine if you were pulling your sister on the sled and you wanted to go this way, but you stood on the opposite side, you would be pulling her backwards. So it's not a surprise then that the angle is negative. Of course, if the angle is, or sorry, the projection is negative. If the angle is bigger than 90, you're going the opposite direction and your projection would be negative. So good news is we didn't have to imagine this picture. The math does it for us. Now let's try and find the component of B onto A. So it's the opposite. This was A onto B. This is B onto A. And it's the component. So I don't care about the magnitude, or sorry, I only care about the magnitude. I don't care about the direction. So the component's still the same formula. It's B cos theta. This time B is 20. The angle between is still 130. And your component is negative 2.9 if you punch that in your calculator. I don't need the units because I'm only talking about component. So why is that one negative? Well, you can imagine that the flashlight is perpendicular over here and it's working backwards, and that's your negative component. All right, so where is projection used? Well, it's used for this classic vectors question. So this is where you'll want to make sure that you pay close attention, because this is the question you'll be asked all the time about projections and vectors. So a classic physics question here. We've got a 30 kilogram box sitting on a frictionless ramp inclined at 30 degrees. So for starters, I want to talk about this frictionless ramp. So we're going to pretend that there's no friction. Because if this were a real scenario, this box sitting on the ledge or on this ramp, it might actually stop and stay there because there's a friction between the box and the ramp itself. And you know the situation where even though you're tilting the ramp, the friction is holding it in place. You can imagine it if you take a textbook and put it on your desk. If you lifted your desk a certain bit, like at an angle, the book would actually sit there for a second. Now, as you increase that angle and you lift your desk up higher, eventually friction loses control and the book slides down the ramp. Okay, so we're actually going to take friction out of these questions. There are questions later on that friction might come in, but today we're just going to take friction out of this and pretend this is a perfectly frictionless surface. So it wants to slide down the ramp. Okay, that's what actually it's going to end up doing. Okay, there's a rope though holding it in place. So this whole scenario is frozen. The rope, there's tension in the rope to hold this in place. The question is, how much tension is necessary to hold it in that place? That's what we're going to figure out. All right. Now, we have to imagine all of the vectors in the scenarios that are acting on this box. The vector that is acting on everything in the world is this vector. That is gravity. Okay, the force due to gravity. Everything wants to go straight down to the center of the earth. Okay? This box, had it not been for the ramp, it would fall straight down. Okay? So that's a measurement we can calculate. We can calculate it in newtons. And it's found by taking the kilograms times a very special number. And many of the physicists who are watching this know that the number we multiply by is 9.8. So 9.8 is the um, force due to gravity. Okay, it's actually a longer decimal, but we're going to use 9.8 as our calculating thing to calculate the force due to gravity. And what you do is you multiply the 30 times 9.8. And we get this thing called 294 newtons. Newtons means um, uh, how much force it is. It's Newton meters. It's the kilometers in meters per second that gets multiplied to figure out your force due to gravity. So what we figured out is that this vector here is 294 newtons long. Now, be careful on this. Sometimes I give you a question where the question is given to you in newtons already. So it might say the box is 294 newtons. So you don't multiply those by 9.8. You just use your 294 newtons. But if it's not there, then you're going to actually have to calculate 30 times 9.8 and get 294. All right, so this vector is going straight down. It wants to go straight down in 294 newtons, but it actually is going down the ramp. So the question is, how much of this force due to gravity is acting down the ramp? Well, that sounds like a projection question. So we're going to project the force due to gravity down the ramp. And we end up with something like this. The projection of force due to gravity, but in the direction of the S vector. So I've called this the S vector, the slide vector. Okay, so I want to know how much of this gravity pull is in the S direction. Okay, and that would result in a vector like this. And it's a projection. So let's use our formula for projection. It's Fg cos theta. The catch is the theta is the angle in between this vector and the direction it's moving. So we need this angle right here. So how am I going to figure that out? Well, what we've actually created is a right triangle. So I'm just going to take a green pen here, and I'm going to show you the right triangle. I'll try my best to show you the right triangle that I'm talking about. Okay, there's the right triangle I'm talking about. Gravity is straight down, so it's going to be perpendicular there, and you've got this right triangle. In this right triangle, I know that's 90, and this corner is the same as the ramp, which is 30. Okay, declined at 30, which means what I'm left with must be 90 minus, or 180 minus 90 minus 30 is 60 degrees. So let's just get rid of that awful triangle, and I know that the angle between is 60. And that angle there is the angle on that triangle that I traced, but it's also the angle up here, right? It's going to be perpendicular because the slide is perpendicular to the, or it's not perpendicular, parallel to the ramp. Okay, so the angle between here is 60. It's the same angle. So if I wanted to figure out the red vector, I need to say it's the force due to gravity, which is 294, cos the angle in between, which is 60. Punch that into our calculator, and we're going to get 147 newtons. So that means the box is actually sliding down with 147 newtons. It's not the full weight of gravity because it's not in the direction of gravity. So only 147 newtons is sliding down. Okay, and so we say, since it's projection, we need to talk about its notation. We could put little s vectors if you wanted, or s unit vectors, but I'm going to say it's going 147 down the ramp. So that's great, except this box is standing still. It's not moving. Okay, it's just sitting there. And that's because there's an equal and opposite force up the ramp that is holding it in place. The question is, how much is that? Well, that is also going to be 147 newtons up the ramp. Okay, so that's called the equilibrium. All right, that's what's keeping it in place, is this red vector up there. It's 147 newtons up the ramp. But my question is, how much tension is in the rope to produce 147 newtons in this direction? So this T value, because it's at an angle, it has to be bigger than 147. If we were smart, we would have tied this rope off at 0 degrees and just have it right here. And the amount of tension we would need was only 147. But because it's at an angle, the t value must be bigger than 147. Okay, so this vector here, we want to know how much tension is necessary. When it is projected down onto here, your answer is 147. Okay, so it produces this other projection question. The question is, the projection of t onto E is what I know, and it's t cos theta. But this 147 is the answer. I want to know how big the t was to produce this answer. So the 147 is the known. It's this side down here. I want to know the t value at the angle of 10 degrees. So I now am going to solve for t. It's being multiplied by cos 10, so I'm going to divide it by cos 10, punch that in my calculator, and I get it's 149.3 newtons of force is necessary in that rope, obviously a little bit bigger, and this will produce 147 up the ramp, which will match the slide down the ramp, and the box will stay still. So the tension in the rope is 149.3 newtons. You can imagine if we had produced, if this rope would have been at a worse angle, at something like 45 degrees, we would need a lot more tension because it's an inefficient way to hold the rope. Okay? And this number would have been bigger. So, recap, calculate your force due to gravity down here, except it's in the motion of the slide. So we're going to project this down the ramp to figure out that it's 147 down the ramp. Since it's not moving, there must be an imaginary 147 up the ramp, the equilibrium. And we need to figure out the larger tension that produces 147, and we figured out it was 149. Okay, so this is going to be our classic vector question. There's lots of twists on this that I could do, but I think for the purpose of what we're doing, we're just going to stop with this, and that'll be enough for you to practice. So today's all about practicing the box question. Good luck.